In this section, we're going to look at derivatives of exponential functions. This goes with section 4.3 in your textbook. Okay, the derivative for your natural exponential function. Okay, first of all, you need to know that the natural exponential function is just e to the x power. Okay, this is the parent function. So, according to our definition down here, the derivative of the natural exponential function is in fact the exponential function itself, unless the exponent up here is differentiable. And if it is, then it will be the exponential function times the derivative of its exponent. Alright, so let's look at example 1. We're supposed to find the slopes of the tangent lines to the graph f of x is equal to 2 times e to the x at the point 0, 2 and the point 1 and 2e. Alright, so if we're finding the slope of the tangent line, the first thing we need to do is find the first derivative of the function. So we're looking for f prime of x. And then f prime of x, this is going to be 2 times the derivative of e to the x. Well, remember that e to the x is its own derivative, so it looks like the first derivative of our function here is itself. Alright, so when x is equal to 0, so we're doing it for this point right here, the tangent slope m will be equal to 2 times e to the 0 power, or 2 times 1, or 2. And then for when x is equal to 1, we'll find that slope of the tangent line. Alright, m will be equal to 2 times e to the power of 1, which is just 2e. And you'll notice that 2e and 2, these are the y-coordinates from these points. Not an accident. Example 2, we're going to differentiate these functions. We're going to find the first derivative. The first one, we're going to find the derivative of e to the 3x power. Alright, so remember, the derivative of our exponential function is the exponential function times the derivative of the exponent. Now the derivative of 3x is just 3. So the first derivative will be 3e to the 3x power. Okay. For part B, we've got e to the negative 2x to the third. So again, the derivative of the natural function is going to be the function itself. So we have e to the negative 2x to the third times the derivative of its exponent. So the derivative of negative 2x to the third is negative 6x squared. So the derivative of e to the negative 2x to the third will be negative 6x squared e to the negative 2x to the third power. Part C, the derivative of 4e to the x squared power, this is going to be 4e to the x squared power times the derivative of the exponent. Well, the derivative of x squared is 2x. So 2x times 4, that's going to give me 8x e to the x squared power. And then finally down here in part D, we're going to have e to the negative 2x. And then the derivative of negative 2x is negative 2. This is going to give me negative 2e to the negative 2x power, which we can leave here, or we can change it to negative 2 over e to the positive 2x power. So either one of those is going to be okay. Alright, example 3. These are going to get a little bit more interesting. We're still going to differentiate. Okay. For part A, this is going to be an e to the first power here. So all of this is a constant. And so the derivative of a constant, remember, is just 0. For part B, let's see, the derivative of e to the 3x plus 1 is going to be e to the 3x plus 1 times the derivative of the exponent there, and the derivative of 3x plus 1 is just going to be 3. So this one's going to be 3e to the 3x plus 1. Okay, part C, you got x squared times e to the x, alright? This is a case where we have multiplication going on, and so our multiplication rule is that we're supposed to do the first x squared times the derivative of the second, this is e to the x, plus the second e to the x times the derivative of the first. Well, the derivative of x squared is going to be 2x. So this one's going to be x squared times e to the x plus 2x e to the x. And you can leave that here if you want to, or if you want to go ahead and factor out that common term there, which is x e to the x, you're welcome to do that. That's going to give you x plus 2. So either one of those will be acceptable. Part D, we're trying to find the derivative of e to the x plus e to the negative x over 2. And I think I had factored out that 1/2 to try and do it this way. Alright, so we've got half of, so the derivative of e to the x is just e to the x. The derivative of e to the negative x is e to the negative x, but the derivative of the exponent up there is negative 1. So we have half of e to the x minus e to the minus x. And if you want to turn that back into e to the x minus e to the minus x over 2, you are certainly welcome to do that. Alright, for part E, we have e to the x divided by x squared. We're going to use our division rule here. Okay, and the division rule is we want to do the denominator, which is x squared, times the derivative of the numerator, which is just going to be e to the x, minus the numerator, which is e to the x, times the derivative of the denominator, well, that's going to be 2x. And then all of this is supposed to be divided by that denominator squared. Alright, so this is going to give me x squared e to the x minus 2x e to the x over x to the 4th. This is actually reducible because if we factor out that x, we'll have x e to the x minus 2e to the x over x to the 4th, and now I can cancel that x with one of those, and we're going to be left with x times e to the x minus 2e to the x over x to the 3rd. And then finally for part F, we have x squared times e to the x minus e to the x. Now conveniently, we've already found the derivative of this up here in part C. So we already know this one's going to become x squared e to the x plus 2x e to the x. That came from right up here. Alright, we just need to take the derivative of that, which is just going to be negative e to the x, and we're finished. That's all there is to that one. I guess if you really wanted to, you could factor out that e to the x power there. It's going to leave you with x squared plus 2x minus 1, but, you know, no real advantage there, just an extra step. So either one of those will be acceptable. Alright, example 4. When a telephone wire is hung between two poles, the wire forms a U-shaped curve called a catenary. For instance, function y is equal to 30 times the quantity x to the x over 60 power plus e to the negative x over 60 power, where x is between negative and positive 30, models the shape of a telephone wire strung between two poles that are 60 feet apart, and x and y are measured in feet. We want to show that the lowest point on the wire is midway between the two poles. how much does the wire sag between the two poles? Okay, so really, if we draw a picture here, we've got a telephone pole here, we've got a telephone pole here. We know that the distance between these is 60 feet, and there is a wire in here that's doing this kind of thing right here. And we want to show that this minimum is exactly halfway. And since our domain is going from negative 30 to 30, it looks like our halfway point is going to be at x is equal to 0. That's what we're going to be trying to prove. Okay? And then we would like to know this distance right here. How far down did it go from where it actually should be? And we can find that by knowing how tall this point is and how tall this point is, and then subtracting the two. Okay. Let's start with trying to figure out that the halfway point, or x is equal to 0, is in fact where the lowest point occurs, or where a minimum occurs. Now, if we're going to do that, we're going to try and do our first derivative test on this. So we would like to take the first derivative of our model there, and this is going to be 30 times e to the power x over 60 times 1 over 60 plus e to the power negative x over 60 times negative 1 over 60. This is going to give me, let's see, we're going to have 30 times e to the power x over 60 minus e to the negative x over 60. And then this will actually reduce because 30 can go into 60. So we'll have e to the power x over 60 minus e to the negative x over 60 power, and then this is going to be over 2. And there's going to be our first derivative. Okay, to find critical points, now we need to take our first derivative and we need to set it equal to 0. So we'll have e to the x over 60 minus e to the negative x over 60 over 2. We're going to set that equal to 0. I think the first thing I'm going to do is multiply both sides by 2. That's going to give me e to the x over 60 minus e to the negative x over 60. And this will be equal to 0. Alright, and let's see, let's add this to the other side. So we'll have e to the x over 60 equal to e to the negative x over 60. Notice the exponent didn't change signs, okay, just this one right here. Now, we have a property that says if you had two exponential functions equal to one another and they have the same base, it must be true that their exponents are equal. That means that x divided by 60 is the same thing as negative x divided by 60. We're just setting the exponents equal. And if we cross multiply to solve, we'll get 60x equal to negative 60x. Alright, let's see. If we add that to the other side, we'll have 120x equal to 0, and then when I divide by 120, we'll get x equal to 0. So there's my critical point. Okay, so I'm almost there because I was hoping to get x equal to 0. Now all we need to do is prove that it's a minimum. Alright, and I can do that. Let's see, let's put some more room in here. Put an empty slide in there so we'll have a little bit of room to work. Okay, so my derivative, we're going from negative 30 to 30. We've got 0 in the middle. Okay. So we have negative 30 on this end. We've got positive 30 on this end. We've got 0 in here, so the interval goes from negative 30 to 0 on this side, and from 0 to positive 30 on this side. We need 2 test points. I want one in this interval and one in this interval. Okay, so I can choose anything I want to between negative 30 and 0, and I'm just going to choose negative 10. but you could choose whatever you want. Okay, and then we're supposed to take that and plug it into the first derivative and determine if we get a positive or a negative answer. Alright, so let's see what that first derivative was. And I found it and written it over here. Y prime is equal to e to the x over 60 minus e to the negative x over 60. This is over 2. Alright, so I'm going to put negative 10 in for x's. So let's see, we got y prime e to, this is going to be e to the negative 10 over 60 minus e to the opposite of negative 10 over 60 over 2. Now remember, all I really care about is whether this answer is positive or negative. So I'm going to put this in the calculator and see what I get. And this is giving me negative 0.167. This is a negative answer. Okay, so that means it is decreasing over there on the left. Alright, now we're going to get a test point on the other side of our critical point there. So something else on the other side of 0 back here. I'm going to choose positive 10, but really you can choose whatever you want as long as it's bigger than 0 and smaller than 30. And I'm going to plug it into the first derivative over here. So y prime is going to be equal to e to the positive 10 over 60 minus e to the negative 10 over 60. And then this is going to be over 2. And I'm going to put this in my calculator and see what I get. This gives me positive 0.167. This is a positive. It is, in fact, increasing over here on the right. And what this tells me is that we have a minimum. At x equals 0. So we've proven the first part of it, the fact that the minimum point occurs halfway between. Okay, so we have a minimum. Let's find out exactly what that minimum is. Okay, all right, and we can find that out by when x is equal to 0, we can plug it back into our original function right here and figure out what y is equal to when x is equal to 0. Alright, and so by putting 0 into our original function, this is what we get. Y is equal to 30 times the quantity, e to the 0 over 60 plus e to the negative 0 over 60. Now, 0 over 60, that's just going to end up being 0, and e to the 0 is 1. So we actually have 30 times 1 plus 1 here, which is going to give me 60, or in this case, 60 feet. So our minimum is 60 feet. And if we go back and look at our picture, we know that the distance from the lowest point to the point directly underneath it on the ground is in fact 60 feet. Now remember what I said, if we want to find out this distance here, how much lower is it than it should be, we need to know that distance. Well, in order to find that distance, I need to find out how far up the wire reaches on both ends there. So that's what I'm going to do next. In my original function there, I am going to replace negative 30, and we're going to see how tall that, or how far up that wire goes. Okay, so we'll have y equal to 30 times e to the negative 30 over 60 plus e to the opposite of negative 30 over 60. And I'll put that in my calculator and see what I get. This is giving me 67.658 feet when I round it off to 3 decimal places. And we're going to do it on the other end too and find out for the other pole, which is 30 feet in the other direction from our minimum. And hopefully we're going to get the same answer here, but we're just going to verify that. So let's see, y is equal to 30 times e to the positive 30 over 60 plus e to the negative 30 over 60. And I will put this in the calculator and see what it gives me. And we do get 67.658 feet. Okay, so going back to look at our picture, the distance from where the where the wire connects to the top of the pole to the bottom is about 67.7 feet. And the distance from the ground to where the wire dips down to at its lowest point is 60 feet. So it looks like the wire sag, or the sag in the wire, is going to be 67.7 minus 60, or about 7.7 feet. Example 5, the demand function for a product is modeled by P is equal to 50 times e to the negative 0.0000125x, where P is the price per unit in dollars and x is the number of units. What price will yield a maximum revenue, and what is the maximum revenue at this price? Okay, let's remember that the revenue function is actually x times the demand function. And so in our case, our revenue function is going to be x times 50 e to the negative 0.125x. Or we could write this as 50x e to the negative 0.125x power. Okay, if we want to find the maximum, then we're going to need to try our first derivative test on this, okay? And so that means we're going to be looking for our prime. Okay. And what I notice here is that I actually have a product going on there. So I'm actually going to have to do the first times the derivative of the second and the second times the derivative of the first. So, alright, we'll have x times the derivative of e to the negative 0.0000125x, which is e to the negative 0.0000125x, times the derivative of that exponent, which is negative 0.0000125. Okay, plus the second, which is e to the negative 0.0000125x, times the derivative of the first, but the derivative of x is just 1. Alright, we'll simplify this just a little bit if we can. Let's see, we're going to get, and I'm going to switch these around because this one's going to be negative because of that one right there. So I'm going to rewrite this as 50 times e to the negative 0.0000125x minus 0.0000125 x e to the negative 0.0000125x. Okay, finally, if we distribute that 50 inside, we'll have 50 e to the negative 0.0000125x minus 0.0000625x e to the negative 0.0000125x. Okay. Now, if we want to find our critical points, we're going to need to take that first derivative and set it equal to 0. So we'll have 50 e to the negative 0.0000125x minus 0.0000625x e to the negative 0.0000. Okay, let's see, we can factor out the e to the negative 0.0000125x, and we'll have 50 minus the this one right here. Okay, now, if we set, let's see, if we apply our product rule, we'll take the first one and we'll set it equal to 0, or the parentheses there. Could be equal to 0. Now, over here, there is no power I can raise e to that's going to give me 0. Remember, 0 is a horizontal asymptote? So that means that this side over here has no solution to it. But we should be able to do something with this one to get to our critical point. So let's go to another slide. And see if we can solve this for x. I'm going to add this 0.000625 to the other side. And then I'm going to divide both sides by it. 50 divided by 0.000625 is 80,000. Alright, so our critical point happens when 80,000 units are produced. Okay. So now we want to know what that price is when we make 80,000 of those units. So we're going to plug this back into our demand function. And our demand function was 50 times e to that exponent there. So 50 times e to the negative 0.0000125 times 80,000, because we want to know what the price is when they make 80,000 units. And remember, I'm going to round this to dollars and cents because this is going to come out as a money. And I'm going to put this in the calculator and see what I get. And it's giving me about $18.39. Okay, so the price that will yield a maximum revenue is $18.39. Now it wants to know what is the maximum revenue. So now we're going to use the revenue function here and find out what the revenue is going to be when we produce 80,000 units. Alright, so we're going to have 80,000 times 50. This in the calculator and see what I get. And again, this is going to be money, so we're going to round it to 2 decimal places for dollars and cents. And it is giving me $1,471,517.77. So that will be the revenue when 80,000 units are made at the price $18.39. The last thing we have to look at is this normal probability density function, and there it is. It's kind of scary looking. You have f of x is equal to 1 divided by sigma times the square root of 2 pi, and all that's being multiplied by e, and that is an exponent over there, y'all, to the exponent negative x minus mu squared divided by 2 sigma squared. And the sigma, lowercase Greek letter, that is this one right here, sigma, stands for the standard deviation for a probability distribution. And then mu, this one that looks kind of like a U or an M, kind of crossed, is the letter mu. It's also Greek, it's lowercase, and it stands for the mean or the average of your probability distribution. Okay. And then the other thing they want to tell you, we have the standard normal probability distribution, and this is what it's going to look like when they let mu be equal to 0 and sigma be equal to 1, when they assume that the mean is 0 and the standard deviation is 1. And this is still a little intimidating, but not quite as intimidating as the one before it.